In our previous unit, we were talking about how do stars evolve if they are similar in mass to the sun. We went through the red giant phase and we said they ended up as white dwarfs. But things are going to be a little bit different when we're dealing with more massive stars. And so in this lecture, I'm going to tell you about what some of those differences are. Massive stars turn out to be really, really important to us as humans because basically most of the atoms in our body come from massive stars. That's where the atoms were made. When I talk about massive stars, I'm talking about stars whose mass is at least 3 times the mass of the sun. Betelgeuse, which we've talked about before, is an example of that. That's Betelgeuse. This is the constellation Orion, where you can find Betelgeuse. It's that star right there. If you find the famous pattern of 3 stars in a line, that's Orion's belt, and this is his shoulder. That's Betelgeuse. Now, we remember that low mass stars, when they fuse everything up to carbon, the electron degeneracy pressure prevents the core from collapsing any further. And so there's not enough gravity to collapse the core enough to make it hot and dense enough to fuse carbon into heavier elements. But high mass stars have more gravity, and they can do this. So what happens in a massive star? Well, the gravity is so huge because they have so much mass that the gravity overcomes electron degeneracy pressure and makes the core collapse even more. And when it collapses even more, it starts fusing carbon into things like oxygen or neon, things like that. And this can continue on and on and on. You can keep fusing heavier and heavier and heavier elements until you get up to the point of the core being entirely iron. When it gets up to iron, that's it. That's the end of the story. As this happens, you start making shells in the outer layers. Now, this picture is totally not to scale. The shells would be way, 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 way smaller than the outer layers. But you start making shells that are fusing different elements. The outermost one is still going to fuse hydrogen into helium. The next one is going to be fusing helium into carbon. And as you go further in, you're fusing heavier and heavier elements. So you end up with a very complex interior structure with all these shells. Now remember, anytime we start fusing a new element somewhere, either in the core or in a shell, we get a big burst of gas pressure. And that pushes the outer layers even further and further out. This is when we get supergiants. Supergiants are kind of like red giants, except that they're even bigger. The reason they're even bigger is because we have all of this extra fusion going on in the middle. So this is where the supergiants come from. Eventually, the core becomes iron. So back to the core for a minute. Now, everything is fused up to iron. And the fusion stops for a minute, and gravity would like to contract it again. But it turns out that there's another kind of pressure. We'll talk in the next lecture about what pressure it is that stops this. The gravity cannot create the conditions that would be necessary to fuse iron into heavier elements. It just doesn't work. You can't make iron fuse. It doesn't happen. So what happens then? Well, gravity does collapse the thing, and the core collapses just completely catastrophically. It goes from something the size of the sun down to something the size of a city, like 20 miles across, in a matter of seconds. So it's very, very, very fast. It's very drastic. The shells and the outer layers, because this collapse happens so fast, they fall in too and they bounce off and then they explode outward. And that makes a supernova. It's a gigantic exploding star. The cool thing to know is that anything bigger than carbon, any atom bigger than carbon in the entire universe comes from this kind of supernova. When the supernova happens, the star spills its guts into space. And all of those guts are made of carbon and iron and oxygen and neon and silicon and gold and platinum and all those different elements. Every atom bigger than carbon in the entire universe formed in a massive star that eventually had a supernova, which means that most of the atoms in your body formed in a star right before it went supernova, which is a pretty cool thing to think about. This is the only place we get any element bigger than carbon in the whole universe is from a massive star that eventually exploded. So, as the famous scientist Carl Sagan used to say, we are stardust. We are the remnants of a star. Now, we can see other remnants of stars out there. We know this happened because of things like this. You can see these clouds of gas in space. These are called supernova remnants. They make really pretty pictures. This is one called the Crab Nebula. And this one is very famous because we know that there was a supernova that formed this one. Now, modern people didn't see this. The supernova that formed the Crab Nebula was observed by humans in the year 1066 AD. Now, who observed it? Well, the Chinese observed it. They're the most famous ones. The Chinese kept very, very, very good astronomical records even thousands of years ago. So they made a record of the supernova. They saw the explosion. They didn't know what was going on, but they saw the star and it got ridiculously bright, so bright that you could even see it during the daytime, and they made a note of it. They weren't the only ones. There were Muslim astronomers in the Middle East who observed the exact same thing. There were even Native Americans who observed this and painted it in caves in the southwest of America. The only people who didn't make any records of it were the Europeans. So what were the Europeans doing in 1066? Well, they were fighting each other. William the Conqueror was taking over England. I guess they didn't really care about astronomy. But everybody else in the world, in the northern hemisphere, made a record of this supernova, and they made very precise records of where it was. Well, later, when we got the ability to see things through telescopes, you look at that exact same place, and this is what you see. Well, clearly, this is the result of the star explosion that was observed in 1066. You can tell that that's what this is. You can imagine the star down in there exploding and making this crazy cloud. So we know that this happens. And just for the sake of pretty pictures, here are some other supernova remnants. I just like them because they're sort of pretty. This one is actually not in the Milky Way. This is in the Large Magellanic Cloud, which is a little galaxy that's orbiting the Milky Way. And this was observed in 1987, very famous supernova. It's the closest supernova that has happened in the modern era. The last one in the Milky Way was seen in the 1600s by Kepler, who you may have heard of from physics class. Very famous astronomer. So just to wrap up, this is something you're going to want to know. This is just sort of taking you through the process of how do stars evolve. You may want to pause this and write it down, or you may want to even just take a screenshot and copy and paste this into your notes. All stars start off with the main sequence, fusing hydrogen to helium in their cores. They all become red giants, fusing hydrogen to helium in shells, helium into carbon in the core. If they're low mass, they lose their outer layers, become a planetary nebula and a white dwarf. And if the white dwarf is in a binary, it may eventually become a white dwarf supernova. If the star is a high mass star, more than 3 times the mass of the sun, it will become a supergiant with all of these different fusion processes in the core and the shells, and eventually it will explode as a massive star supernova. And in the next few lectures, we'll be talking about what happens to the core after the supernova.